Hartford, after which he went to US and then he did his PhD at University of Massachusetts. And then after that, he had postdoctoral stint at ICTS for 2 years. Then after that, he is at Penn State University, first as a postdoc, and now he is a research assistant professor. And he has been working on different aspects of this multi-messenger gravitational wave astrophysics with neutron stars and white dwarfs. Can you tell us more about his work? Please, Rahul.
Thank you, Santan. I'd really like to thank Santan and his group here for inviting me and give a talk here. So, my work is on computational modeling of different kind of observables that comes from white dwarfs and neutron star mergers, and it falls under this broad classification that has become very popular in last 8 years or so. This is called multi-messenger astronomy. So, yeah. So first, I'll briefly describe my research career. So I started in my graduate work. I worked on binary white dwarf merger and more specifically hydrodynamical simulations using Newtonian gravity, where I studied that after merger, when it forms white dwarf and the disk system, which comes from the disruption of the secondary white dwarf, then what kind of instabilities are active in the disk, and that leads to what kind of transients. So that was my first work. I also work on different kind of another kind of transient, which is known as type 1ax, which is also the origin of which was not clear at that time and still is a little bit of puzzle, and we proposed one mechanism from that. But today I'm going to talk about mostly neutron star mergers and data analysis problems related to neutron star mergers. So in this work, I worked on numerical relativity simulations of neutron star mergers, which requires us to solve Einstein's equation by defining an initial value problem, and also transients from neutron star mergers, which requires us to understand the decay of or heating because of the radioactive elements and its escape into optical and ultraviolet and infrared photons. I worked on data analysis aspect at ICTS and also at Penn State, where we want to understand what kind of matter lies in the core of neutron star and what can we extract from gravitational wave astronomy in general multi-messenger astronomy. So multi-messenger astronomy, of course, didn't start with gravitational waves. It started with our sun. So we have been looking at the sun since antiquity using visible light. It took us a while, a lot of time through critical questioning to understand that other spectrum or other kinds of lights which are invisible to our eyes are the same as electromagnetic waves, and this gives us different picture of our sun, as you can see here. But most importantly, after we understood the generation of energy in stars, which is nuclear fusion through the work of Hans Bethe, it was predicted that there will be a certain amount of flux coming from the theoretical calculation from the sun. But and this led to building of neutrino detectors. But when they tried to measure, they found 1/3 of the flux as predicted from the theory, and that led to big puzzle, so known as solar neutrino problem. And it took us several years to understand that, and led to discovery, in fact, that neutrino are not just a single species, and they oscillate between different species as they travel from sun to earth.
What is the meaning of this multi-messenger?
So multi-messenger is simply that there are multiple messengers coming from these astrophysical objects. And so similarly, electromagnetic waves, which
these are kind of, for example, of that.
Yes, so electromagnetic waves that comes from the sun are one messenger, and neutrinos that come from the same source is another messenger. And we can understand gravitational waves as completely opening new window that is coming from different dynamics and our understanding of different laws, essentially Einstein's equation. And that leads to a pinnacle of multi-messenger astronomy in recent years, which is JBLU 17/17. This was a binary neutron star merger observed by LIGO collaboration. So here, what is shown here is in the first plot is the frequency time diagram of gravitational wave, where the color represents the power in certain frequency at a given time before the merger. So 0 is the time where they merge. As you can see, the power in the frequency at which the most of the power resides keeps on increasing, and this is known as chirping behavior, and this is simply a reflection of the fact that when neutron stars are merging, they go to increasingly high frequency just before merger. But we were very lucky with this event because within 2 seconds after this merger, we also see a large bump in the gamma ray flux. Just a minute.
Quick question.
Yes.
So, do you know that this is neutron star merger from the masses involved, or are there other ways of knowing that it is neutron star, neutron star and black hole?
Yeah, that's a very good question. So, these other aspects of the same other observable from the same source actually ensures that these are not binary black holes.
Other meaning radio and
Yes. So
also,
yes.
which what should be a typical signature of neutron star?
Yeah. So this was since this was the first observation. We also see a gamma ray burst associated with it in the location, and this even before this, it was predicted that neutron star mergers might be source of short gamma ray bursts. But this is the first time we saw them simultaneously. At least, I mean, with some delay, 2 seconds. And after that, after a few hours, from day to 7 a week time scale, we also see optical transients. So here are a spectrum of the transients seen at different times, so 1.2, 1.4, and 2.4 days through different telescopes, and these also show these transients essentially show that the heating, the light that is coming from these neutron star merger is coming from the ejecta that is thrown out after the merger. And this ejecta contains radioactive elements of beyond iron. So heavy elements, mostly lanthanides, actinides.
So this is about using multi-messenger method to identify what are the object features.
Exactly. Object, what are the states of the matter, how gravity behaves, or matter behaves in such a strong gravity.
These Oscar viewers will change the two masses of the binary.
Yes.
If anything remains same, or this is a universal curve?
No, this changes. So if we use more compact objects, let's say binary black hole, this chirping becomes very fast. This time scale of this, where it is order of seconds, it will become millisecond. And if we have a very low mass black hole, then this becomes very long, and this part of it will become almost constant. So for example, if you take 1D white dwarfs much before merger, there will be almost constant frequency, and we will see also constant frequency diagram, and then very late it will curve, and it just slowly. So the reason, and this leads to the name nomenclature, that one of the things that we measure just by looking at this frequency diagram is called chirp mass. That basically tells us that how quickly it chirps. The higher the mass.
One can see this curve in numerical simulation.
Yes. And
Two different, I mean, all masses, I mean, let's take curves from all type of masses combination.
Yes.
Do there exist a scaling in between all these curves?
Yes. So on the very rough scale, to a rough approximation, this chirp has chirp mass to the power 5/3, if I'm not mistaken. But there is a scaling that comes from simply if you take 2 point masses which are rotating around each other, you can calculate the gravitational wave strain from this, and that goes as chirp mass to the power. I'm mistaking the power. It might be 5 or 7/3, but there is a scaling there. That
is in post-Newtonian approach.
Yes.
What are the other corrections?
So other corrections changes only the phase of the gravitational wave. So gravitational wave had two polarization, H plus and H cross. So you can write it as H plus I H cross, make a complex number, and then you can write it as amplitude and e to the power I phi. And other corrections, for example, neutron stars, when they get deformed, that changes the phase, not the amplitude. It changes the amplitude very minutely, so we will not be able to detect whether there is a matter there by looking at the amplitude, but looking at the phase. And the data analysis aspect of gravitational waves ensures or requires us to make that phasing correction very accurate, so that we can derive energy from it. So that leads to this point of mine, which is that this event was also a success of large-scale numerical A2G simulations. because this was all the hints of this was already predicted through NR simulations, but also we after analyzing the data, we have been able to put constraints on some of the matter properties there. And so this was very sort of very big success for numerical relativists, for example. But we didn't see any neutrinos from it, and that was also predicted from NR simulation that neutrino flux will be very small from these neutron star mergers, so as predicted. But we hope to see neutrinos from these neutron star mergers, and then we'll learn much more about the matter conditions.
They go very relativistic, right? In order to be detected.
Yeah, the neutrinos are, of course, all relativistic. When they
In
when
the
they
jets, when they are emitted,
so from neutron star mergers also they are highly relativistic flows, and all of them will be.
in the medium, you don't think that there can be interactions on the weak that can.
Also,
be
there is a lot of
dissipated as-
so there's a lot of interactions of neutrinos at the merger. Neutronic flux are so strong that they affect the dynamics of matter. So currently we can incorporate it as some effective viscosity that acts in the matter. But then there are higher order treatment in the computation. For example, solving Boltzmann equation along with fluid equation that we know. But they affect there. But once they escape there, then. So,
Is it true that number of neutrinos is roughly equal to number of light from the photons? You said it will be very low. Is that because the interaction cross section is low that we don't expect to observe them, or is it because numbers?
so the luminosity, when we like in CGS unit, like when we can plot the light curve from these units, and they are low in the sense that we cannot see them here, like on the.
But why? Why are they not comparable? Of course, neutrinos are very deeply impacting the
Yeah.
sea. We detect a lot fewer, but if you remove that aspect, don't you think that it should be roughly equal to the photon? Like flux of photon, flux of neutrino.
When they are created.
Or at the position of the earth. When they're created and position of earth.
If they are created, then intervening mediums or anything can happen. But
No, nothing will happen without it. Light has made it to building.
Yeah, no,
So I'm just puzzled by what is the situation? Is it like the flux of neutrinos is small or a detection?
detection is of course much bigger.
Detection of flux is very, very small.
But if
But if you remove that,
yeah,
like just ask, what is the flux coming to earth? Shouldn't they be comparable?
so there are about 10 to the 45 ergs per second. At the
What is
conversion,
the
the number
ratio of number of neutrons and number of photons?
Yeah.
Would that be close to one?
I'm not sure.
yeah, right.
Why not? They are pretty massless, photons are massless.
The flux is predicted to be low. But what makes it low? I mean,
So the way we model it is simply the matter which contributes beta decay, those are emitting neutrinos, and in very rough approximation, people just escape it. Like they just say it doesn't interact, let's just let it go outside the medium. And that gives very low flux. I'm not sure like how it looks like. Of course, there will
But
be.
it comes from beta decay. Neutron has 8 minutes decay time. Now with the relativistic system, highly boosted system.
Yeah.
It will dilate. Number of beta decays will reduce. It will time dilation.
Yeah, so that's Jonathan is pointing out, it's deeper me interest in production cross section, then it will be very separate. So the question is, what production cross section was there? Anyway,
Thanks for the question. So that is just representing noise. So when you observe it, you have noise and the signal, and that this will always be there.
So do we have data only from call or does it do?
It goes further up to yeah 3 minutes.
3 minutes.
Yeah. So LIGO starts looking observing any gravitational wave at 20 hertz, and from 20 hertz to it goes up to 2000 hertz.
So in principle, if LIGO has the sensitivity,
yes, and there are future detectors proposed where they are looking to that.
so you answer to my earlier question, so we can tell it's neutron star because we see all the things.
Yes, Yes, that's the telltale
If it's
sign.
any of the other kind, they would not see the one.
Yeah, but the one critical thing is neutron star black hole merger. That because that also involves disruption of neutron stars, and that can also produce some of these transients. And
And then the question goes back, how do we know that?
yeah, so one is mass ratio, another is I mean, to be honest, this problem is still not completely clear, but there are indications.
It is clear that it has to be neutron star neutron star.
Yeah, so for example, if you see mass ratio 3 and you see electromagnetic transients, and neutron star mass is 1.5, but there can be no neutron star of 4.5, so it has to be black hole. But some of these things are very subtle, because then people have theoretical models where they can construct a 4.5 solar mass neutron star. I'm just giving an example. So those things makes this data analysis aspect very subtle.
That goes to that equation of state, right?
Yes,
Right.
yes.
So there are some viable equation of state which can produce these 4.5.
I will just give you an example, but currently it is 2.9 from the theoretical UV calculation, but it can go up to, because of rotation, or 3.1 and so on. But more than that, yeah, not possible. But that was it.
And this is consistent with what must be.
Oh, this was very close to 1.8, 0.9 solar mass. Yeah, this was very close to 1.
And it cannot be white dwarf, right?
Yeah, it cannot be white dwarf, because so one of the thing about gravitational waves is that the more compact the object is, the closer it will come at the time of merger, and stronger the amplitude will be. And white dwarf merge at the millihertz frequency, and those will be observed in future mission, which is laser interferometer.
LIGO is not even sensitive.
Log is not sensitive to that.
The second one is one is the gamma ray.
Yeah. Second one is also same, observed through different instruments. So these are integral, these are quasi. I'll come back to some of these pictures later. So I'll just reiterate that that multimessenger astronomy allows us to affirm our understanding of fundamental interactions and gravity, and also leads to discover of new fundamental properties of matter, of forces, interactions. So hope through gravitational wave understanding is to reveal the true nature of gravity, and how gravity treats other forces. But we need to be very careful when we test the gravity or nature of gravity in these tests.
You don't mean something other than the Einstein.
Yeah, that's
it. True nature of
that's the hope, that Einstein's theory breaks at some point. That we know for sure through singularity theorem by Penrose. But does it break at the scale of when two black holes are merging? And is it the black hole at the stellar mass or very small mass? So those things we might see. So that's what I mean.
But even in the gravity side also, there are like all this post-Newtonian approximation may not be a very good approximation.
Yeah, but in
the masses ahead.
Yeah, but currently what we do, we solve any initial condition of the neutron star merger through full Einstein's relativity. So through nonlinear GR. So what the signal that we are producing, or the model that we are producing, is constellation with full GR. So post-Newtonian approximation is used for initial waveform modeling, but near merger and just post-merger is a full GR.
Full GR. So you cannot use templates just from the Newtonian post-Newtonian.
They are used, but initial for the in spiral regime. Yeah. For example, for neutron star probing the matter, those are fitted with NR simulations. So those are consistent with full GR. I mean, as best as we can do. Of course, there are a lot of physics here that people slowly will incorporate through in the computation, and they will slowly.
All this radiation damping and everything is taken into account.
Yeah, these are. Okay, so first, very brief survey that the stars, which are atoms of in astrophysics, leads to three end states: white dwarfs, neutron stars, and black holes. The very massive star leaves very short line, and they end up as black hole. Intermediate mass stars lead to neutron stars, and then white dwarfs. The boundary between these two. So one of the outstanding problem in astrophysics is to find out how to map masses of initial or main sequence stars to the white dwarfs, and not only masses but also properties. For example, what mass and metallicity of initial main sequence star will end up white neutron star or white dwarf. These boundaries are very blurred, and through observation, gravitational observation, through population statistics, we hope to actually disentangle this problem. So I'll discuss about two main objects, which are white dwarfs and neutron stars. White dwarfs are essentially both are supported by degeneracy pressure, at least in some regime. In the case of white dwarf, these are electron degeneracy pressure coming, and the core is mostly helium, carbon, oxygen, and neon and magnesium, depending upon the masses. In neutron stars, in the outer crust, these are iron and heavy elements. But just below crust, we have neutron, proton, electron fluid in beta equilibrium. And below that, it is still a question of, it's still an open question that what kind of species can exist here, what kind of baryons and even deconfined quarks can exist or not. And this is one of the unknown that we want to find out. So essentially, how do we do? We construct stars. So here is a cartoon where I have constructed a spherical shell at radius r. These are Newtonian stellar structure type diagram with rotation and magnetic field. But in these equations, I will ignore rotation and magnetic field. So the first one is just simply saying how mass changes from inside out, and the second one is telling me how pressure changes. And these two together, when the surface at which the pressure, the point at which the pressure becomes zero, we define as the radius of the star, and that is what observable is from for neutron stars. The third one is the equation that determines the perturbation of the star. So from Einstein's equation, we perturb both metric and the energy momentum tensor, and we obtain that how when you put a neutron star in a tidal field of another neutron star, how it gets deformed. And this computation of y through some formula gives us what we know as tidal deformability of neutron star. So tidal deformability is like Young's modulus. So when we stretch an object, it undergoes a strain. So the ratio of stress and strain we consider to be property of matter. Similarly, here when we calculate the tidal deformability in neutron star, we consider them as property of matter. It depends on what kind of matter is there. And these equations must be supplemented by equation of a state. And by equation of state, what we mean is a.
Sorry, so what was y again?
So y was the perturbation of the metric. So when we take Einstein's equation, G mu inside the neutron star, yes. And we calculate this y at the surface r, and then that quantity is used in a formula to calculate love number, which gives us.
So which component?
So yeah, that's so we what in these calculations what is done is we say that the perturbation, which is full 4x4, we could take only even parity perturbation. So and when you take even
Parity, but it is not that.
what is only the diagonal terms.
Only
diagonal terms. Yes. And so that those are determined by these four functions, but when you put them into perturbed Einstein's equation, ultimately it comes down to only one function.
So which is perturbed? Rho and P, right?
So rho and P is perturbed on the left hand side,
Oh, right.
but on the on the right hand side, left hand side, we perturbed metric.
Yeah, which component? Which are the one, which perturbation?
So this is, so we take the full perturbation, but only the even parity part, not the full, only the even.
What does that mean? It's a 4x4 thing, right?
0, 0, 0, y or I.
That's right. Yeah, that's what I'm.
So if you take the diagonal terms, there are four functions.
That's right.
So all four functions could be arbitrary, but when you put them in perturbed equation, it turns out that only one function determines this. Others are related to perturbation.
Four given in terms of
One function, and why
that is the condition of what's even.
even parity. Yeah.
What does that mean?
I mean, mathematically, I understand it only the diagonal terms. I think, yeah, to visualize it, yeah.
Is that general? In all the four diagonal elements, the perturbation is parameterized by only one variable.
Yeah, that simply comes from the perturbation equation. So when you
If general perturbation is like that,
That's what it is.
general perturbation, yeah,
but even then, even parity is general.
No, it's something important. Right? Even parity
Gauge
is.
kind of conditions should be there,
Huh?
right? Gauge should be there. The rectangular gauge should be applied. After that, even and outlet should be.
yes.
So the gauge condition should be applied, and after that, you consider that the diagonal component will be.
Yeah.
You have this, you have P plus 2, you have 10.
Yeah.
Then you have 4.
In general, you cannot decompose it, even parity and odd parity.
What I'm saying is that finally you are left with two scalars and 2 tens tensors and vectors by removing all the coordinate conventions. So we probably using some other simultaneous argument to just leave it at one. Why? Whatever you say. So these are the non vectors, right? You are just changing the scalars.
You mean the from the metric?
Yeah. So y is a scalar or it is?
Y is a scalar.
Okay.
It is so the perturbation it belongs to it scales as h prime over I h, where h is the perturbation in the matrix. So the y tends to double is
It will only one scale.
That's the perturbation, but what about the background? So that is some spherically symmetric? or-
Yeah, background is determined by these two
And that's
equations. I mean,
spherically symmetric.
yeah, spherically symmetric in this case.
But what geometry? Spherically symmetric. Yeah. okay.
So the metric is determined by the matter, this row inside, such that it matches to Schwarzschild.
But this is not a black hole.
Yeah, but outside,
Meaning the vacuum condition
yeah, vacuum solution. Outside it has to match.
of the spherically symmetric stuff.
Start, yeah.
Okay.
And point out, yeah. Sorry. Okay, so this leads to our main question that in this equation state, which is essentially a pressure density curve at 0 temperature, we take, then there is a one-to-one correspondence between pressure density curve and mass radius curves, and also between tidal uniformity and mass curves. So and these are below. We are looking at the white dwarf mass radius and tidal uniformity mass curves. Since white dwarf equation states are known to a very good accuracy, we have just here one curve. But neutron star, we have degenerates. We don't know which of these curves are actually true in nature. So we get different mass radius curves. So traditional X-ray astronomy gives us the measurement of mass radius. So it gives us posterior in this plane. Gravitational waves have started giving us posterior in this plane. And that's how it is an independent observation and gives us extra constraints on the equation state. Okay, so now I'll come to the compact binary system. So there are many different kind of compact binary systems that you can construct, starting from making different mix of white dwarf and neutron stars. And so I'll talk about only binary white dwarf and binary neutron stars, although other kind of transients are also very interesting and can be studied using the same computational framework that I've been using.
So the equation you showed is applicable for all three.
Yes.
Even black hole.
Black hole interior,
Okay.
yeah,
So
we
then
don't know.
how do you get the third one?
You mean the black hole?
Yeah.
So in the case of black hole, we have only space time.
Right,
So
outside.
when we do outside, inside we don't do any evolution.
So
So
those equations were written down for inside.
inside, yeah.
So you're going to do the white dwarf one.
Yeah, so I will talk about binary white dwarfs and binary neutron stars.
Sorry. Third one, black hole white.
Yeah. Those systems exist, but yeah, I have not studied them. So I just wanted to point out just brief, in my research career, I worked on these two, and I find a lot of similarities between these two systems in terms of physics that is active there. So in both of these systems, white dwarf and neutron stars, the lower mass system, which is usually bigger, gets disrupted and forms an accretion disk around the more massive object. And these accretion disks then leads to many instabilities inside them, and most notably gravitational and magneto-rotational instabilities. These are the instabilities that comes from self-gravity and magnetic field that is present in the disk. And so I will show some examples of gravitational stability that is active in the white dwarf, and that has also been studied in the neutron star case. The other similarities, which was very striking, which I pointed out in one of my paper, that white dwarf mergers leads to type 1a supernovae. These are electromagnetic transients powered by nickel 56, decay of nickel 56. And kilonovae are also powered by radioactive decay of R process elements, which is rapid neutron capture elements. But both transients can be modeled by this model, which is developed by David Arnett and then generalized by Chertopoulos and Wheeler, which is essentially homologously expanding ejecta, and there is some heating going on because of the radioactive decay. Okay, so very briefly, I will reiterate the point of data analysis. So here I'm showing a gravitational wave signal from 150914, where the signal has been shown in as observed in Hanford and Livingston, and these are the frequency time diagram of these two sources. On the right, however, I'm showing you the correct the signal that we actually see, which is this very small signal buried deep within the noise, and this basically forces us to use Bayesian inference to extract parameters of these systems. And what Bayesian inference demands on the first hand is to construct a precise model of the signal, and that is parameterized by the system's properties. For example, masses, as you were asking, like masses and different properties of matter, like different equation state. And once we put that, then we get the correct signal, and then only we can extract what are the systems that we are observing. So when we observe gravitational waves, because of the point particle, if you observe them to be point particle, massive particle, and in spiraling, then we get a gravitational waveform that we can construct using post-Newtonian and as well as full NR. But when neutron stars are when they come, these objects, when they come very close to each other, their finite size effect start becoming important. So that means they get deformed, and then because of this deformation, the quadruple emission from the gravitational waves changes, and that leads to different waveforms, and that can be parameterized by tidal deformity of both neutron stars. In this case, we parameterize them using effective tidal deformity, which is a combination of two tidal deformities, lambda A and B, and their mass ratios. So in gravitational waves, we obtain the effective tidal deformity, but what we want to know is tidal deformity of individual neutron stars, which will give us the constraints on matter. So this is done using this way. We define symmetric and asymmetric component. I apologize here. The symmetric has to be plus and asymmetric is minus. It's changed. And so using these symmetric and asymmetric component, there are relations proposed in the literature which says that asymmetric, tidal deformity, and symmetric are related by this function. These are essentially fitting formulae given to a collection of equation states. And similarly, a fitting formula is given for compactness. So how this allows us to find out neutron individuals?
Sorry, this is not be non-zero in the data, or is there?
So these are purely theoretical fitting. So what we do, we assume many equation states curves, pressure density curves, and construct lambda mass curves, and then we in the literature, Yagi, Yunis, and they put all the curves on the same in the same plot, and they find that they lie almost on this line, this fitting formula, and that is what is proposed as universal relation. But of course, each equation state is different.
Sorry, I'm asking a difference. This tidal deformity.
Yes.
Is it not zero from the data?
Oh, from the 17 or 17.
From any neutron star.
Yes.
Like
Yes.
neutron from
Yes.
black hole. It is not zero.
Yes, it is
And
observed.
it's a clear signal that it.
Yes. Yes.
But tidal deformity actually constrains the equation of state.
Yes, and so that's what I'll describe. So essentially, so what we do, once we have this universal relation, it allows us that from single lambda tilde parameter, we can find out both individual tidal deformities and also find the radii using this second compactness lambda relation. But using this universal relation, this will bring some bias compared to the actual equation state, and this is what is mentioned here as these double-headed arrows, which says that for each equation state there will be different kind of biases that will become because of these universal relations. So in one of my work, I worked on like removing this bias when in future detectors, when we observe very precise DNS mergers, then we need to take this into account. So I will show this diagrammatically here. So let's just focus on the left hand side for clarity. So here, what I do, I inject a population of DNS mergers using this equation state APR3, the blue curve, and then I use universal relation, which is used by LIGO, to find out the radii, and then I find that all these black dots are the results of that. which essentially tells us that for lower masses, they recover the radium, but for higher masses, there is a large bias. So what we proposed is that that instead of using this universal relation which represents all equation state, let's just first constrain what equation state is present in there. So first, let's do model selection method, and for that we need to take that bias into account. So we need to do this for each equation state. So when we obtain the data, these mass radius curves, first we will ask, let's suppose if this equation state is present in the data, then what is the evidence of that? And then I'll answer this question for each equation state. And once we find the equation state which has the strongest evidence, then we know the full mass radius curve, right? Then we know the radius of any system.
What is this data? So this is simulation.
So this is simulation. We do.
So what are these error bars in program?
So error bars. So essentially, when we do the parameter estimation, we obtain the posterior distribution. Data is a distribution, and so essentially these error bars are showing me the statistical error that distribution.
What's the black and what's the pink?
So the black one is the one where I use the universal relation used by LIGO, and the blue one is the one where I correct for it.
The blue is more realistic.
Blue is more realistic. Yeah, which takes into account the difference between universal relation and any particular US.
I understand correctly, this API relation is API many-body interaction.
Yeah, this is Akmal Pandey. Yeah.
But there actually you have this higher mass neutron star.
Hmm.
So they claim that there may be they take into account two-body interaction. There can be three-body, four-body interactions become important at higher mass neutron stars. So these equation of state don't have.
I see.
Does that also bring this mismatch and this?
So in our work, we consider several mass radius curves, and we just treat that as a model of equation state. So we don't go deeper into asking this question like what physics and which is more realistic. From our perspective, we just treat at different models, and then we can constrain them. If there is another model of equation state which gives me some different mass radius curves, that can also be incorporated in this analysis.
These will start failing at the higher mass.
I see.
Radius is almost constant.
Yeah.
Because then all this multi-body interactions become important.
I see. Okay, so essentially what I do when we observe these different data points, I construct different mass radius curves using those data points. Then I calculate this quantity called chi-square, where each data point is compared with the model radius and then weighed by the statistical error. And this chi-square, and we do this multiple times, so it has a distribution. If my data is the model, then this chi-square will be smallest. And I found that if so in this lower panel, I'm plotting this chi-square distribution for these three models. So in all of this, injection is APR3. The hatched one is the one where if you use universal relations, and if you do this model selection, you'll get the hatched ones, which says that ALF2 and APR3 both are degenerate. It has not been able to distinguish, but when you include this correction, then APR3 is clearly stands out. So
Which
yeah.
correction?
So
the
the
non-universal.
US specific.
So you do not consider any correlation with the data. You're just using the diagonal down the
Yeah.
I don't think that should be met.
Correlation between different neutron star events.
No, the data points, the sigma. So you are just using the diagonal down of the error matrix, right?
So these sigma are the errors of each radial posterior of different events.
Of different events. So there is no way they are correlated.
But even for seeing for each PNS system we get two sigmas, but they will be correlated. Yeah. So but I consider them independent.
And using prior information on those parameters.
No.
So these are just the post you use flat priors.
Yeah. These are, so in this case we are doing this kind of frequentist model selection method, but this can be translated to basic and percent now. Right now.
So in your data you consider also larger than 2 solar mass transistors.
Some of them, yes.
But if you remove them, then does it improve your price?
Yeah, so I'll come to this point just in the next slide, which is that, so when people talk about neutron star, usually people are talking about 1.4 solar mass neutron star radius or 1.2 solar mass. but equation state is a curve, right? So we cannot do point estimates. And this is one discussion which is completely missing from the literature. And I pointed out that if two curves are overlapping, for example, these two, then no matter how many events you observe here, you will not be able to distinguish them. You need to observe some events here, and they may not be, in the nature. For example, 2.4 solar mass is not there, or something. So the model selection criteria, whatever we come up with, has to scale with F2 distance. If two curves are very close to each other, then we will not be able to distinguish, right? Unless our error goes below such a range. So this will always be there, because we will always have some error. So we can always constrain equation state with some error. So that answers of your question, that yes, if we have some very high masses, then that will be useful for constraining some equation states. Yes. So in future, one of my work, what I'm leading into is that many new gravitational wave detectors will be proposed in future, which will have different radius constraints. So for example, here this is cumulative distribution plot of radius errors that we will see from different events. So you have multiple bineutron star merger. For each mergers will be at different distances, so their errors will be different. So their uncertainty in radius measurement will be different. So that's what this cumulative distribution is. And here the letters essentially represent the combination of detectors. So for example, HLVKI represents Hanford, LIGO, Virgo, Kagra, and India at advanced configuration. And E and C represents Einstein telescope and Cosmic Explorer. And these two together, for example, ECs together has best radius uncertainty, as you can see. So it can go even below 100 meters. Although at that point, we need to consider several modeling aspects. For example, proper modeling of crust, if neutron star is rotating or not, and these things. So, but when we do better than 100 meters, it is generally believed in the community, although I'm not an expert, that below 100-meter constraint will tell us something about nuclear constraints on the nuclear properties or properties of the nuclei that we see here on the Earth. Oh, y-axis is just cumulative distribution, CDF, cumulative distribution function. So it goes from 0 to 1.
What is the radius of that?
So how well we can find out the radius of individual neutron stars?
Of the entire neutron.
Yeah. Because we'll see.
You mentioned this pressure going to zero is very thing, but it goes to zero asymptotic.
So for neutron stars, there is a crust. It goes very rapidly.
Very rapid.
Yeah.
And it actually reaches zero.
Zero means industrial medium density. Yeah. So, but these are very subtle point, because so in computational work you cannot put zero density at one point. So people put very high density. But these are some of the challenges in computational work that one needs to take care. But currently we just not take care. Yeah.
So right now the experiments are.
So this one is HLVKI plus is the least sensitive instrument, but this is also in future after like 5-10 years or something.
Right now the uncertainty is around
1 kilometer. Yes, that's what we have.
So tell me again what the uncertainty is. So if you are given an equation of state, how well can you determine this? Or is it an observational?
Observational. So given a bineutron star margin or a population of margin,
Right.
how well we can constrain neutron star area. And
With
so
a population.
population of such margins.
They're given an equation.
Not given equation state, just from that. I mean, yes, in the sense, because we'll do the model selection, then we will obtain the radius. Yes.
Okay.
So in some sense, it is telling us how well we can constrain equation state.
Which is saying something about the experimental sensitivity.
Yes, experimental sensitivity and also actual population that we will observe.
How many?
Yeah, how many we will observe, and that is scaled according to current LIGO estimates. So currently we have observed 1 BNS signal, probably 2. So we scale that, and in some volume, so we scale this to very large volume that we observe, and then we say that if you observe so many BNS signals, then we can constrain. Then this is the distribution of radii.
Is this saying anything about numerical simulations also, or this is completely independent?
It is saying in some sense, because the waveform that we use to constrain the tidal quantity is coming from numerical simulation. So that also needs to be, yes. That is saying what that also. Okay, so as I said, like some accurate modeling, aiming for less than 1% error requires accurate elastic crust modeling, and some data analysis aspects also requires modeling of gravitational waveforms. So one such concern is what is known as dynamical tides, which simply says that if neutron star comes very close to each other, they also start oscillating, and this frequency of the oscillation is comparable to the binary frequency. So that requires full numerical modeling. At some point, it will become full nonlinear, and we just need to simulate it and then obtain a model.
What is oscillation?
Neutron star.
Oscillation in radiance?
Yeah, just general oscillation of the spherical body. When these neutron stars are very far apart, they are in quasi-circular orbit, so they're coming very close to each other very slowly. So another way of saying is that whenever they experience higher tidal field, they quickly oscillate and settle to a configuration. So their orbital frequency is much smaller compared to these frequencies. But when they come close to each other, they are also oscillating and also rotating. So this leads to some non-linear changes in the waveform that we cannot predict by hand. We have to use NR.
Is that in some phase relation with
Yes.
the orbit and the tidal oscillation?
Yeah.
Or are they coupled in something?
They are coupled. So the way to do it is what people do. People write the Lagrangian of these two systems, and then there will be a new term added, which will have a property like 1 over omega minus omega, like orbital frequency, and omega that is the neutron star oscillation frequency. And there are different frequencies of neutron star oscillations. So those all of them will contribute slowly, but
They can get some resonance.
yes, and that's why this 1 over omega minus omega is coming.
Cannot they see?
No, they have not been seen so far.
Why not? I mean, if it's such a big effect,
Because we have seen
that merger, we have seen some effect of it.
So we have seen only one event, and that merger also data. I'd not say was such a good data that we can claim that. Like some people even argue that we have seen matter or not. It was still consistent with black hole. But fair belief is that yes, we have seen matter, imprints of matter, but more we need more accurate data for that. Okay, I have not much time, but okay, so I'll describe the main merger and post-merger evolution of neutron star. Essentially, what happens is when these neutron stars are merging, at the time of merger, they come at a very relativistic velocity against each other, and this leads to shock and ejection of lot of matter. So this disruption neutron star is someone known as dynamical ejection of matter. They also leads to formation of black hole. So when these neutrons are merged, they form this hypermassive object because its mass is much larger than what can be supported by that equation state. But since these are rotating, they remain as a hypermassive object. But then they can collapse to form black hole at several different time scales. So this whole time scale is considered to be about tens of seconds. But this merger and then ejection of jets and collapse to black hole, these happen within 3 to 4 seconds.
So you said in your simulation you use no rotation.
Yes. Yeah.
But that may be a very bad approach. I mean, these might be very rapidly rotating.
These might be, but one like comparatively fair belief is that neutron stars, when they are born, and especially pulsars we are seeing, they extract energy from rotation. So slowly they will lose their rotation after a very long time, and this gravitational waves time scale of merger is very long. So by the time they'll merge, they will lose their rotation and also magnetic field. But if you ask me personally, I think these are essentially computational people's idea of simplifying the problem. So we must include all these things.
No, but whatever is the index,
Hmm.
that
yes, that will get the rotation from binary to momentum.
and you neglect that.
No, that is not neglected. That is not neglected. So that is treated full in full GR. Yes.
And also, the neutron stars before merging, they can also, like some of them can be different pulsars because they are in a binary system. Some of them might have been recycled.
Oh yeah, so recycle pulsar, that's a very good point. This is something that I am pursuing. That these recycle pulsar, how if they merge, then what happens? But remember, the cycle pulsar also get their rotation from accretion from some
Yeah.
giant star, right? And if there is a neutron star, binary neutron star, that means that star has also undergone supernova explosion and formed a neutron star, and that will also again take billions of years to come to closer, right? So
You're saying they might again.
yeah, so astrophysically that problem is probably not that interesting, but theoretically one should pursue that. Even if you see one or two events, it will give us a lot of knowledge.
The use angular momentum because of emission of radio.
Radio waves, yeah, these
For long period.
yeah, these electrons which are spiraling along magnetic field lines, they emit synchrotron radiation and they extract energy from the radiation. Okay. So essentially the full picture is that here it is summarized well. Here is that two neutron stars, when they merge to form this they disrupt and form this hypermassive object, and then they lead to either black hole or neutron star with an accretion disk, and then it can lead to also highly magnetized neutron star, and all the ejecta that is going outside outwards from this system are shown here in blue and red, and then they are what powered as electromagnetic transients. And then these matter, when they hit the interstellar medium or sweep the matter in the interstellar medium, they are observed as radio waves. So on the top, all these signals at different time scales are also shown. So the current practice here is that we use we use computational model to connect the final observable to the initial parameters. So for example, I will ignore these first bullets. So let's focus on Einstein's equation. What we do, we start with two neutron star with a given equation state. So we have two masses and some equation state. We do the full merger, and then we obtain all these signals. We obtain gravitational waves. We also obtain electromagnetic transients and radio transients. And then we find these, because these are the observables, and then we connect how these observables theoretically, computational model are related to the initial parameters. How it scales with respect to, let's say, total mass, or equational state property, which is like maximum mass or something like that. And these scaling are then inverted from observations to find out the property of matter or some initial parameters. So in one such work, I was asking this question that if we start with two neutron stars where you have M1, M2 and equation state, then what is the condition that leads to prompt collapse? So as shown here, two neutron stars merge to form black hole at different time scales, or of order of 1 millisecond or order of 10 to 20 milliseconds and so on. But I was asking this question, what is the equationist condition that leads to prompt collapse to form black holes? So how do we determine the prompt collapse observationally? Why is it interesting? So prompt collapse means that when so these on the bottommost panel, I'm showing gravitational wave strain as function of time. So earlier it is shown the spiral where the amplitude keeps increasing, and then in the case of prompt collapse, there is no post-merger signal. However, in these two cases, there is a post-merger signal. So these are classified as prompt, and these two are as delayed collapse. And on the middle panel, I'm showing maximum density. So as they merge, the density increases, but because of the oscillation of the objects, there is an oscillation in the maximum density. And on the top, what is shown here is the minimum lapse. It is a field that is defined in when we do 3+1 decomposition of Einstein's equation, and that is also characteristic of whether maximum density or whether black hole has formed or not. So lapse going to very small number means that black hole has formed. So
what's the signal for collapse in your?
So first signal will be that we will not see any post-merger gravitational wave signal. So we'll see that neutron star merge, so we'll see signal and then suddenly blackout. But if there is no prompt collapse, then it will merge and then we will see a post-merger signal. So there will be gravitational wave signal.
But nothing about your whatever
electromagnetic transients.
The density or pressure.
Yeah, those are not observables. Those are just
in your simulation. Will they show some?
Yeah. So these are the simulation results, but these are not observables. Observables will be gravitational waves and also electromagnetic transients.
I guess I'm asking about your variables in your simulation. Which variable will show that it is a collapse state?
Oh, so these ones, minimum lapse. These are proxy to formation of black holes. But when
minimum lapse?
So
it should be, you showed the T equation, right?
Yes.
So those are your
So those are equations for the spherically symmetric object, stars. But this is lapse is a field that is defined when you do 3+1 decomposition. So when you
So you're no longer doing those equations.
no, these are full Einstein's equations solved numerically, and this is one such field that is evolved with time. And we what you're plotting here is the minimum of that field in the whole domain. And when this falls below this point 2, this is rough criteria, then we say that black hole has formed.
Yeah, you're taking infrastructure points like.
No, these are full finite size objects and along with the equational state. So it's evolving with the full.
So this point 2 is agreed upon, but you have some comment there which
Yes.
says that it is collapse.
Yeah. So this note is a subtle aspect where what it says is that since Einstein's equation is invariant or covariant under coordinate transformation, right? So when you do this 3+1, this lapse depends on our choice of coordinates, or is our choice. So this falling to point 2, it's a gaze dependent number. But how can we show that a gaze dependent number is showing us some invariant property? So the correct way to do is to find out that at every time slice when we have a full field, we have to construct what is known as apparent horizon. We have to find the apparent horizon in the whole data. And once we find that, then we say yes, black hole has formed, and that is invariant statement. But in many of the simulations and the gaze that we have chosen, we find that lapse falling below point 2 is consistent with formation of apparent horizon that we have checked through a couple of simulations. So it is safe.
But if you want, you can go and check for
Yes.
the present, which you do, or
We don't do. We
but
do.
you're sure that that's what.
Yeah, we do it for few of them, and then we also check labs. So we say okay, yeah. Because these are very expensive.
But here the equation of state will also change when you're close to the merger.
Yes. So what we do here is that we take a collection of equation states. These are all different equation state mass radius curves, and we simulate all of them with different masses. So here all these dots are the ones that we take 2 neutrons having that masses, and then we merge them. And when we see which of them forms black hole properly and which one of them don't. So we find that above red dot is the one that forms black hole, and the below are the ones which do not form. Then we find that this red dot, which is the kind of threshold mass for the collapse formation, changes with equation state, right? And that's our idea, that we want to find something about the equation states.
Sorry, more collapse, I mean, there should have been something about equation of states, so maximum, density you can support or something.
Yes.
There should be some signal. Is
Yes.
that not also where we check in the simulation? That is
So for us, when we construct the maximum mass for equation state, it is static and spherically symmetric star. But if it is doing oscillations, then we're not sure, right? And these are highly dynamical state. So to really find out whether it will collapse or not, we have to evolve it for a long time. But here we are asking question when it collapses immediately, and is that even meaningful? Way to find
But
something very
independent of oscillations or and all that, there should be some maximum that any given equation of state should be able to support, right? Some maximum density, independent of any oscillation. At any point, if you cross that density, it should not be able to support.
No, actually, so in Einstein's theory, that is one of the puzzle, interesting point that matter in itself or rest mass density is not enough. The other parts of the energy momentum tensor, momentum flux and energy fluxes, those are also important, and they also gravitate. So we need to know full.
That's given in each one.
Yeah.
And you can check, including those, you can check whether it is.
But these considerations will lead you to find out the apparent horizon essentially. Yeah. So apparent horizon, the identification of apparent horizon
Is a global surface, or is it like local?
this is defined only on one spatial slice.
Okay.
Yeah, this is defined only in one spatial slice. And if you combine all these apparent horizon in different time slices, these form what is known as I forgot the name. So essentially, the event horizon that we call of a black hole, that is a global concept. Like to find that, you need to backtrack all the geodesics.
That's not what we.
That's not what we mean. So these apparent horizons are only time slices, and we can combine them, and then we can construct something invariant over a time period. and that is done. That is usually done.
So in the Einstein equation, you have this TB union.
Yes.
TB union is dynamically changed,
Yes.
and that TB union,
Generally, the projection of TMU on the spatial slice. That is what changed, because these are like four by four, like 4-dimensional covariant picture, but we have to do 3+1, and then we get the spatial velocity of the fluid and momentum flux and energy flux and so on. So those are three changes. Yes.
this back couples changes the
Space time. Yes.
This time you are talking about, that is the local time or asymptotic of it. What is it?
Yeah. So
We know near the, I mean, heavy of there, like Rahul time slows down, right?
yes.
So what is it?
So when we do 3+1 decomposition of Einstein's equation, we consider one time function. So this is a field that is defined over all space, and that is what lapse function is. So lapse function which is changing from time to time. So when you take dt, like 1 delta t time at any time, you can use lapse function to find out that if time flows this rate at this location, then how it flows at this location. Lapse function in some sense is giving you that variation of time flow of the observers. Okay. So in that work, was essentially what we asked this question, that this threshold mass must be proportional to equation state. Like maximum mass. If equation state supports larger maximum mass, then this threshold mass must be larger. And this proportionality constant itself is asked to be proportional to C max, which is the compactness of the maximum mass neutron star. So once you combine these, then you get this relation of R max as a function of M threshold and M max. So please note that this relation, this K threshold is proportional to this is a hypothesis, right? And when we do the numerical simulation, we can test whether it is linear or not, or what kind of function it follows. So we did that, and then we find that yes, these are roughly linear, and then we find these coefficients A and B. So in this final function, A and B is coming from the solving Einstein's equation through full nonlinearities, and then we plug them back here, and then we obtain these constraint equations. So in this case, what we are showing here is that it's a constant R max contour that is plotted here in the space of M threshold and M max, and then on top of that we plot several constraints. So for example, this left-hand side constraint is coming from the heaviest neutron star that we have observed, so that its maximum mass has to be larger than this. This upper constraint is 2.9 solar mass, which comes from causality. So when you construct equation state, you can pose this constraint that sound speed has to be less than the speed of light. Then you get maximum mass 2.9 solar mass, and then you get this constant R max contour. And then after that, and then there are several other constraints that can be put on this, which is coming from the compactness limit of the neutron star. So neutron stars cannot be arbitrarily large and cannot be arbitrarily small. Another way of saying that their compactness has a range. And since we don't know the equation state, then for each our equation state choice, the range is different. And that was not taken into account in literature before. So in this paper, what we looked at is that that if you put these constraints of compactness, lower and upper limit, then we get this wide region which is allowed. And in future, we hope to put constraints just by observing prompt collapse or not. So for example, 17 we saw a kilonova signal, a transient from it. That means it was not a prompt collapse. So that means threshold mass has to be larger than this. So lower part is ruled out. And then I put here some other hypothetical bineutron star merger systems and the constraints coming from this. So essentially, when we observe more events, we will constrain the maximum mass in some smaller regime, and then we will constrain the equation state with that. So going ahead, in one of the work that I'm pursuing currently is essentially trying to put the constraints from gravitational wave observations and nuclear physics on the same footing. And what it requires is to construct an equation state model, where in the classical sense we can write it as kinetic energy part of the equation state, where all these fermions are their thermal motion is supporting contributing to the pressure or energy density, and then potential part, which is coming from the interactions. So in white dwarfs, generally this kinetic energy aspect is the dominant. There is very little coming from the interaction between the electrons. But in neutron stars, these become very important, at least in the deep core. In one such model, this potential part is expanded as using some coefficients, EIs and BIs, and that can be put into one-to-one correspondence with these parameters, which are observationally determined from electron scattering experiments on the nuclei as well as heavy ion collisions. So, for example, these last two parameters are coming from the heavy ion collisions, and these are parameters which is coming from the electron scattering experiments. So these are pure nuclear matter and then symmetric nuclear matter. That is.
Where does it go?
So this this epsilon potential, this thing can be expanded in two ways. One is this, another can be expanded around the saturation density, and that's where these parameters come. So these are essentially derivatives of I think energy function, if I'm not mistaken. So first and second order derivatives. So when we do the Taylor expansion, so by constraining these
In terms of the density.
in terms of density,
Baryon density.
yeah, baryon density around saturation density. So what we're doing currently is that we take these different equation state, which has different values of these parameters, and then we do simulation. That we will see gravitational waves, and once we will have actual observations, we can probably put constraints that what values are these. So there is a range of these values, these parameters that we know currently from experiments, and probably hopefully we can constrain them more.
But these you are assuming that your neutron stars that you observe are near the nuclear saturation.
Yes, and that's a big extrapolation, and this is one of the biggest criticism. But this is what the state of the art is currently. We do not have full handle on how to put constraints on like nuclear experiments or electron scattering experiments with neutron star. This is not clear. It's not clear to me.
That will be difficult because your neutron stars are too nuclear.
Yeah,
density.
yeah, very good. Yeah. People have done similar studies for core collapse supernovae where they have extrapolated this. But yeah, all of these can be objected strongly. Okay. So briefly, I'll describe this is a repeat slide, basically saying that transients from white dwarf merger and bineutron star mergers are very similar in nature. So in one such work, I asked this question that type 1a supernovae are used for distance measurement because they are standardizable in the sense that they have a correlation between their intrinsic luminosity and the decrease in luminosity. So I asked this question, can this also exist for kilonovae and can they be used for distance measurement? To do this, I used the numerical activity simulation. So here I'm showing the ejecta mass on log scale for binary neutron star system. So this is M1, M2 plane of two neutron star masses. And this in the same plane, I'm also showing ejecta velocity. So when you take the numerical activity fit formulae and the kilonova light curve models, then you can produce all these different light curves. And these light curves also show correlations like type 1a supernovae, which means that they can be used for distance measurement. However, when we will observe more kilonovae, then we will be certain whether such correlations are real or just purely theoretical. But at least there is a hint that they can be used.
The shades are what?
So these colors represent the ejecta mass on log scale in solar mass.
Log of what?
So log of m ejecta divided by solar mass. So like a red is around 1, -1. So
And the X and Y axis are also covered.
X and Y axis are the masses of individual neutron stars. So each point in this space is one BNS system, binary neutron star system.
Okay, so the deepest cover is what, 1 meter?
4.
Four.
Yeah.
It can be bigger than just the sum of the masses.
So this is -4. So on log scale that is 10,
log.
10 to -4. Yeah. So yeah. One very interesting work that I did with a student at Penn State who was performing simulations of QCD phase transition during the mergers, and in this work I collaborated by producing the kilonova light curves signals from such mergers, and we found that these when there is a phase transition, so this BLQ is the one which has phase transition in the equation state, and the BLH is the one which doesn't have. So when there is a phase transition, its luminosity is always weaker, is dimmer than the when without phase transition. So if you see a kilonovae, you see multiple kilonovae, and we see their luminosity dimmer than the expected, then this might be hint of QCD phase transition.
What is the typical temperatures?
So temperature reaches up to 60-70 K MeV. Yeah.
You mean the phase transition during collapse?
During merger. So when it merges and then it happens. There could be phase transition before merger also if the masses are very high. Yeah.
So those are zero temperature phase transition.
Those are zero temperature, yes.
That will be very different from this.
Yeah, those will just change the neutron star structure and tidal uniformity. So the signature of those we will see during its spiral. So the initial part of the waveform that we see, we can just use that to constrain that, and we can use the merger and the post merger to constrain this kind of constellation.
But the equational state already has this information on which phase.
Yes, in this two pairs they have done that. So in the temperature density plane, so what we do in our simulation is that whenever the condition reaches that state temperature density, we just convert them to quarks in certain fraction, and that leads to some softening of the matter and
So it's a
different
jump
dynamics.
change from one equational state to another.
So for not for all density temperature, so these two matches up to certain density and temperature, but beyond that they differ. So that's why we do two different simulations. In one of them we don't do phase transition, in other of them we do that. So, but I'm not sure how, like I'm not sure about the theoretical understanding that how this phase transition like is like.
So when you're doing this simulation, at some point you might get to a phase transition, right?
Yes.
Then you have to change the equation.
Yes.
Do you do that? Or?
Yeah. So the one in which we allow phase transition is a completely different simulation than the one in which we don't allow.
But realistically, you should allow if it goes to that.
Yeah, if we believe that, but that is precisely what we want to change, because in simulation we can always not allow it.
Yes.
Artificially.
And usually it is not allowed. Is it?
Usually not allowed, yes. Like in the normal.
Carrying out phase transition. You don't know the.
Yeah. No.
No, and the zero zero temperature. There is no phase transition. Then these are at finite temperature.
So then if without that, if it matches the data, then can you conclude the phase transition is not happening during the class?
So that is precisely the reason for this simulation, that we want to see how the signals differ, and they differ in a very subtle way. Yeah, it's not clear. Yes. We have just put out a paper on data analysis aspect. So if you have because these two signals are very close to each other, so you need what kind of data analysis aspect you will use, like how a strong signal you need to actually conclude this, and this will be clear actually in next 10-20 years. It will take time. Okay, I'll skip this part and I'll take just 5 more minutes to describe my work on binary Dwarf mergers. So when these binary Dwarf mergers they come close to each other. So in this cartoon I'll show, this is also similar to a neutron star. So they get deformed. So this white dwarf, the larger one, is the lower mass white dwarfs, and it is getting deformed because of the tidal. This is simulation. These are the SPH simulation, that's a smooth particle. These have been done by Lauren Aguilar and Enrique Garcia. These are not my simulations. And at very late time, when they get completely deformed and it completely disrupts the secondary white dwarfs and it forms an accretion disk. We are looking at from the side these objects. So what I do after that? Oh, sorry. These are Newtonian solutions. Yeah, these are Newtonian solutions because white dwarfs are much less compact, so we don't need to actually do. So what we do after that? So that So essentially these white dwarfs, so this here I'm showing the schematic diagram of binary white dwarf merger evolution. So when white dwarfs first takes some masses from some lighter white dwarf or main second star, but at the late time when it merges, it forms a white dwarf and an accretion disk, and then it leads to an accretion disk evolution on very long time scales. And this is the stage at which I have contributed, where the many instabilities in the disk that is present because of the rotation and also magnetic field that can be active here. And so I've shown in my work through a series of papers that these disk instabilities are very important. You want to understand the accretion onto white dwarf and its explosion. And some of the problems related to these systems on these time scales involving magnetic field is still open, and that I want to pursue in future.
So in the simulation, the picture, it didn't seem like there was this.
Yeah, so because we are looking at from the side. So what I do after that is I take that data, which is come from SP simulation, and then I initialize it into Eulerian grid, which uses finite volume schemes. And the reason is that finite volume schemes for solving fluid equations are much more accurate than SPH. It can resolve shocks, and if there is a burning, that it can also resolve that. So essentially, and it conserves momentum on the global scale. So it is much more accurate in that sense. So I take that data and then I initialize it on the Eulerian grid, and that's what is shown here. So here in the central there is a white dwarf, and then the accretion disk that formed is around it, and this accretion disk is as massive as central white dwarf. And because of this self-gravity, this leads to spiral shocks that goes outwards from this, and then that leads to mass accretion on the white dwarf. These are the same instabilities that leads to spiral structure of our galaxy, or any galaxies, for example.
Sorry, like the central mass is one of the main dwarfs to begin with.
Yes, central.
So if the masses are equal, why is one disrupted than the other?
So not exactly equal. These are 1.1 and 1.0 solar mass.
Yes, they're
But-
very close, so why should one be disrupted and one?
Because of this slight asymmetry. Even if you take exact same masses, because of the numerical condition, there will always be slight disruption. So if let's say
Equal.
if
I
you
would
take
have thought that it would be maximally disrupted, both of them.
and that's what we see.
1.1, it should go towards that, right? Both will get disrupted, but one is like.
Yeah.
It seems like not in that.
So these are all numerical aspects, but I think this is physical. So between 1 and 1, the one getting disrupted is physical. But if you take, let's say, both one, then again you will see one of them disrupting more or earlier than the other, and that is numerical. That is numerical in the sense that
Numerical artifact.
numerical artifact. So because there is always some numerical noise, and which so for example, just to give another example, if you initialize the white dwarf on a grid, it should just sit there, but then it does oscillation, and then sometimes it evaporates and so on. So those are all numerical
And how
artifacts.
can we trust any of the
Because those numerical artifacts are controlled. Those are very small, so they leads to essentially momentum conservation violation. Or yeah,
Now,
sure.
What he is saying is that there is a perfect asymmetry, and you are seeing asymmetry at later time. Then you have to see whether it is numerical, and that is what they.
And here I can trust some of them.
In other results, there must be some control way to check that they are.
Yeah. So all these numerical codes must be checked that how accurate these are, and they are tested against analytical results. So you can start with so for example, all these codes are tested against demand problems, which is just high density and then there is a density jump, and then you let it evolve at t equal to 0, and there is an analytical solution of that, and then we check how different the numerical solution is compared to the analytical, and we see that these are very close to each other, like 10 to the power -6 or something. So then we trust them, but of course when you incorporate all the physics pieces like Poisson solver along with these Riemann problems, then to check all this you need actual experiments, and that we can do only for terrestrial fluids, not for astrophysical fluids. But for terrestrial fluids we have tested that for many of them. So essentially in this work we found that these instabilities were active, and then we found then later people also found same so here what we are looking at is the explosion of the white dwarf because of this mass accretion. These white dwarfs start burning very rapidly, and then they become type 1a supernovae. And so the same instabilities, then people further observed in binary neutron star mergers, and this was very important for the ejecta mass in neutron star mergers as well.
And you can match this with observation of type 1a supernova, whatever you can.
Yeah, so that's also a good question. So far from the white dwarf explosion, first of all, there is this open question that when we take a white dwarf, it starts burning. The first burning is subsonic, and then it becomes supersonic, and that is what known as detonation. So deflagration to detonation transition. We have not been able to do this realistically in our simulation. We see this happening in nature, for example, oxygen and hydrogen gas, but for white dwarfs, we have not been able to do this in simulation. So people detonate white dwarf artificially, and even those supernovae do not satisfy the correct observational criteria. So this gap is still there.
Yeah, the best simulations still are not yet.
Not completely. Yeah, some of them will lie on the what as Phillips relation, but not all of them. So they do not satisfy Phillips relation, but their light curves are close to supernovae that we see.
In that stretch factor, maybe I'll talk to you.
Yeah, sure. So last point I want to explain is that, so we also looked at oxygen neon and carbon oxygen white dwarf merger, and these are very hard to detonate. So there is a outburst in the disk, and that leads to some production of nickel 56, very small amount of nickel 56, but that leads to a transient. And we predicted this in 2018, this transient, and then after 2 years, there was one observation of a remnant. This is a remnant in our galaxy, which has been observed, and there was oxygen neon observation in the spectra from this remnant. And people hinted that this might be coming from the oxygen neon and carbon oxygen merger, that model that we predicted. And then later, after 1 year, there was another type 1ax observation that was, so this blue curve is data published in our paper, a theoretical model, and the red is the one that was observed in 2021. And this also was hint that our model is on the right track. But this came to us a very big surprise, pleasant surprise, that there was another supernova observed in 1181 AD by Chinese and Japanese astronomer, and that is also believed to be consistent with our model. So there were 3 different observations of type 1a supernova. So believed to be because these have been observed in 1181 AD, and they are the magnitude, like how bright the light curve was and how long it was observed. How long it was observed is noted at
that time.
Yes. Yeah, it was observed. It was observed.
So it was,
Yes.
There for a long time.
Yes.
Some few days.
Yeah, even 1000 AD, in 1000 AD, people have seen supernova happening in our galaxy that are mentioned in cave paintings.
I observation is how accurate is that?
Yeah, so their location is supposed to be very accurate. Their time scale is supposed to be very accurate, but the brightness is the one that is usually taken very differently.
There's a record of the brightness.
A record of the
As
brightness.
days go by, how the brightness
Yeah.
change, they have recorded it.
Yes, they have observed, and that is usually done compared to some reference star, just like Parker did, and supposed to be fairly accurate, but I don't know the details of this field known as astroarchaeology. Yeah. Okay, I'll skip this part and I'll just finish with this slide that I can't thank enough the people working on the numerical solution of partial differential equations. This is a field which requires many subtle aspects of different fields like approximation theory, PD, hyperbolic PD theory, and also coding. Actually coding and making it work. That's a very big work, and all these equations, the Euler equations, gravity radiative transfer, and especially Monte Carlo simulation is a very general framework that is useful in all of the physics and beyond, even engineering, right? And it is still a challenge, and that's why many people call it art of computational modeling. Is that like what meaningful conclusion we can draw from this simulation? It is always a concern that the result that we're getting, is it physical or is it numerical, like as we discussed, and this remains always a concern. But there have been examples where we have actually discovered something new from the simulations. And on the right hand side, I'm showing that the need to actually be more mindful of our programming practices and computational work. So here in this work, in this recent book, the author shows that if you write a serial program on your laptop, you're using only 0.8% of resources. So actually efficiently. So if you are if you want to, so another way of saying is that our computational resources will always be limited. We'll always get some certain amount of code. Even if you combine whole computational resources of the world, it cannot not solve everything of all the physics. So we have to find out that how can we use whatever is available to full efficiency, and that is one of the also my prime concern. So I'll finish with this slide where I'll like to acknowledge my collaborators and also students and grant supports. And I'll say thank you.
Okay, if not, we can just discuss.
Yeah.
Thank you very much.
Okay. Stop. Right?
Yeah.